In this video, I'm going to show you how to solve trig equations. So our first example is going to say solve sine x plus root 2 equals negative sine x. So what we can actually do in this particular problem is we could move some stuff around. I actually have a couple like terms. I have sine x and negative sine x, which means that I can actually combine them. So I could do that one of two ways. I could move this over to the left-hand side by addition, or move this to the right-hand side. And I'm going to do the latter. I'm going to subtract this sine x from both sides because I want them combined. And when I do that, these are going to cancel. I'm left with root 2 equals negative 2 sine x. So remember that this is a negative 1 sine x and this is a negative 1 sine x. And when you add them together, you get negative 2. So we want to get sine x by itself, which means I'm going to have to divide out this negative 2. So I'm going to do that to this side as well, which means I have negative root 2 over 2 is equal to sine x. And we're going to need our unit circle at this point in time. We want to know where sine x is actually equal to negative root 2 over 2. And that happens to be in a couple different places between 0 and 2 pi. In other words, one full circle. It happens when sine is negative, so we're in the third or the fourth quadrant. So our two answers are actually going to be when x is equal to 5 pi over 4. I actually do get a value of negative root 2 over 2. And I have another solution that is x equals 7 pi over 4. Now, these are our two main solutions, but notice in the very beginning of this problem, it didn't specifically say that this is from 0 to 2 pi. And remember that sine has that wave that goes like this forever and ever and ever. So there are technically infinity amounts of points where that function is going to be negative root 2 over 2. So how do we actually tell that to our readers? The way that we do that is very simple. For sine and cosine, our periods are within 2 pi radians. So what we're going to do is we're going to do this plus 2n pi at the end. And n just represents a number. So the next value, beyond 5 pi over 4, I would plug in 1 for n to see what the next one is. So it's just 2 pi units away from 5 pi over 4. That's going to continue that pattern throughout the remaining of this function forever and ever. And we're going to do the same thing here. So if it doesn't tell you specifically that you're from 0 to 2 pi, you have to include this part. It's very important that you do. It's telling the reader that there are infinitely number of solutions. You start at these two x values, and then from those, you just keep adding 2 pi units away from them. Okay, let's take a look at another one. Okay, so example 2 says to solve this equation, 3 tangent squared x minus 1. So we want to get tangent squared by itself first, which means we're going to want to add this 1 to both sides. And now I'm left with 3 tangent squared x equals 1. And now we're going to divide out this 3. And I'm left with tangent squared x equals 1/3. And then lastly, we have to get rid of the square, which means we're going to have to square root both sides, which is going to leave me with tangent x equals, and now we take the square root of each part. So the square root of 1 is just 1. The square root of 3 is root 3. But we're going to have to rationalize this. So we're going to do times root 3 times root 3. This is going to get rid of radicals in the denominator. So this is going to be root 3 over 3. And the first thing that we want to check in our unit circle is between 0 and 2 pi first. Notice that this is not in the immediate instruction, so we're going to have to expand this just like the first problem. So we're going to have this happen when x is equal to two different values. The first one being pi over 6, and the second one being 5 pi over 6. Now, tangent does not have a period of 2 pi like sine and cosine. Tangent has a period of 1 pi. So that means we're not going to add 2n pi, we're just going to add n pi to both of these. Okay, so we keep adding a single pi unit to both of these, and that will give us all of our solutions for this. So these are our two answers for this problem. And we're going to keep on going. So our next one is going to be to solve this equation. Cotangent of x times cosine squared x equals to cotangent x. Notice that in this problem, unlike the previous two, we have more than one trig function. So the best way to do these, if you have multiple trig functions, get everything on one side. For instance, I'm going to subtract this 2 cotangent x from both sides. What that's going to leave me with is cotangent x cosine squared x minus 2 cotangent x equals 0. The reason why this is helpful is because now I have cotangent here and cotangent here, and I can factor that out. So what we're going to do is we're going to say they have a cotangent x in common, and this is where I'm going to open my parentheses. So I need cotangent x times cosine squared x to give me the first full term here, minus 2. Okay, now what we are able to do at this point in time, this is just like a factoring problem. We're going to set this piece equal to 0 and this piece equal to 0. So we're going to have cotangent x equals 0. We're going to solve that part, and then we're going to have another equation, cosine squared x minus 2 equals 0. So we're going to solve both of these at the same time. Now, cotangent of x is equal to 0 only in one place, between 0 and 2 pi, and that is at pi over 2. Okay, for this one, we're going to have to add 2 to both sides first. So I'm going to have cosine squared x equals 2, and now we have to square root both sides. So cosine x equals root 2. And that happens when we have, oh, I'm sorry, this is plus and minus. We don't have an actual value on our unit circle for this. And that creates a serious problem. Root 2 is greater than 1. Cosine doesn't go any greater than 1 or any less than -1. So this actually provides no solutions over here. This part is not going to give me an answer. So the lesson that we have to do is go back to cotangent and add on that n pi business. Cotangent, because its sister is tangent, also has a period of pi units. So we're going to say this is pi over 2 plus n pi. That is the only solution that we're going to have for this problem. Okay, let's move on to the next problem. This says to solve 2 sine squared x plus 3 cosine x minus 3. Now, this actually looks like a quadratic function. I have a squared term first, a linear function second, and a constant last. The problem is that I do not have the same trig function, so we're going to have to change them. And at this point, we know that sine squared is equivalent to 1 minus cosine squared with our Pythagorean identities. So we are going to actually have to convert this before we even worry about solving it. This is 1 minus cosine squared x. That's what I'm replacing this with. Okay? Now we're just going to bring down the rest of this, plus cosine x minus 3 equals 0. We're going to distribute the 2 to simplify. So we've got 2 minus, oops, I forgot something in there. That should be a 2 as well. 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. And I actually have a couple like terms. I can combine the 2 and the -3, and that's going to give me -2 cosine squared x plus 3 cosine x minus 1 equals 0. And before we can even bother factoring this, the first term can't be negative. So we are just going to negate all of our terms by multiplying them by a -1. Okay, you are always welcome to do that. When you do that, this becomes +2 cosine squared x minus 3 cosine x plus 1. So now we're going to go through our factoring, and if this gets too complicated because you see the trig functions in there, replace them with x's temporarily. They're just going to later be replaced with cosine. For example, I could say that this is just 2x squared minus 3x plus 1 equals 0. If that's more helpful, then please do that. That's okay to do temporarily. Now, this is where we're going to have to multiply our a and c terms together, which is going to give us a 2. And the only factors of 2 that we have are 1 and 2, which hopefully add up to 3, which of course they do. And it looks like we're going to need a -1 and a -2, so that yields a -3. So we're going to rewrite as 2x squared minus x minus 2x, and this is coming from these two numbers right here, -1 and -2. And then plus 1 equals 0. Now, once you get to this point, we do our grouping, and we just factor. So 2x squared and x have an x in common. That's going to be 2x here minus 1. And out of the next one, since the first term, our 2x is negative, we always want to take that out. But that -1 is going to be the only thing in common that both of these have, which is going to make this 2x minus 1 as well. And you know that you guys do this right when these two are the same, which they are. So that's going to provide us with one of our answers, 2x minus 1. The remaining values, x minus 1, are going to give us the other. So we have to go back and replace these with a cosine. So we're going to come back up here, and the first binomial, this 2x minus 1, is 2 cosine x minus 1. Okay? We need to set that equal to 0. That's going to be the first part that we solve. The other part is going to be cosine x minus 1, and that's coming from this second binomial. Okay, so the first part, I'm going to add 1 and divide by 2 to simplify, which means I'm going to end up with 1/2. So I'll figure out where cosine is equal to that in just a moment. And then the next one, we just have to add 1 to both sides. So we need cosine x equal to 1. So it looks like we're going to have several different solutions here. So after we do this, the only thing left to do is to figure out where these happen. Okay, so cosine x equals 1/2 when x is equal to pi over 3. And of course, cosine is in terms of 2 pi units as a period. So we need plus 2n pi. This also happens in another place, and that is at 5 pi over 3. And that also needs a plus 2n pi. The last one is when cosine is equal to 1. And that actually only happens in one place, which is 0. And although it's still a 0, if we still need to add on this 2n pi, which you could very simply rewrite as that it's just 2n pi. So this is our first solution, our second, and our last. And that will conclude this tutorial.